Hello, everyone. I'm just testing up the sound and voice here a bit. Can you hear me? I can see Thomas is in the car now. Is everything working for you?
Yes, everything's looking good, Vang. Hi.
Yes, I think it's working good. Can you also hear me?
Yeah.
Yes.
I think I didn't hear the last part someone was talking. Oh, the screen is wrong. Swap display, yes. Yeah, okay. Exactly 2 o'clock. I will. I think because we have the the list of accept invitation is more, so I will wait a couple of minutes more, so everyone can join in. Maybe I will start by mentioning some practicality first, and then repeat it once more when we have more attendance. Well, what I want really to bring your attention is that this webinar or workshop will be recorded, and we will probably publish on the Claudia website or AI for the People website, or on the private, the YouTube channel for Claudia. So if you have some issue with that, I mean, not having your self be recognizable in this recording, then either mute the audio or turn off the camera, or I mean, in the very extreme case, just to mention for the sake of completeness. So if you are totally against recording, then I have no way to ask you to leave the workshop. Yeah, that is how we are going to work on this workshop. Yeah, we have 22 people now, and according to the list, we have about 40 that either accept the this invitation or say maybe they can join. So I will keep just 1 minute more, not too much. I mean, maybe because of some technical problem that they cannot get on time. I mean, also welcome everyone who are here already. Yeah, the attendant list keep increasing, so that is an indication that we should give a bit more time. And all right, I think we can start this. And so again, welcome. My name is Vang Lê Quý. I'm a special consultant in data science in Clara, and I'm also a member of the technical working group in AI for the people. And I'm also the ambassador for NVIDIA Deep Learning Institute, which can give you a free course, access to the paid course from Deep Learning Institute. So yeah, and I would like to repeat the very important point about this webinar or workshop will be recorded, or actually now being recorded. So if you do not like yourself to be recorded or recognized in this recording, then please turn off your camera and mute your microphone. And in extreme case, then leave the workshop. And that's because we are going to publish this on the website in the, for future viewer to see. Yes. The next point is that I would like to introduce a bit, explain a bit about why we make this series of workshops or webinar. The name of this series is the Interesting Topics in AI. And by interesting, we mean something really practical for use in your research, and maybe some hot topics that the community, the professional community is talking about, or something that is really demanding for our works or projects. And we try to keep the topics in an organized manner, so they hopefully can be interconnected in a way that makes sense. And also we want to, through this workshop, help you make the best use of Clara resource, including support, servers, and also data science service. And also, there are a lot of tools in the open source community and companies like NVIDIA and so on, that it is a really good idea that we have a good grasp of what they are, and then use it in your research, and also make the best use, in turn, make the best use of the hardware, software, and service in Clara, and also AI for the people. And we are thinking now making it monthly or bi-monthly. And I will send out a poll soon to hear your opinions. It depends, because sometimes if you, most of us cannot make it in monthly, or we cannot ourselves organize monthly, then we will do it bi-monthly. But I mean, a regular schedule will be the best for us to remember and come back and continue and deepen the discussion. And the organizer of the workshop will be NVIDIA, AI for the people, Clara, and maybe some future partners. And the next one is some short, really brief introduction about AI for the people. And hopefully Thomas can give some words about a couple of minutes about what AI for the people offers.
Yes, can you hear me, Vang?
Yes, I can.
Okay, good. So Thank you, Mark, for that. I'm chairing the AI for the People Center, and on behalf of the center, I would like to thank everyone for participating today, and of course, especially NVIDIA for doing this. We're very happy about this. And I presume most people know about AI for the People, but in case there are newcomers, welcome. The center is an AAU center which has a number of goals. Most profound is perhaps that we want to increase the knowledge and competence level within AI across all 5 faculties at the university. And we do that using different means, and one of those being, for example, workshops organized as this today. And of course, I'm happy that this is something that Bang has organized together with NVIDIA. So we are actually not playing that big a role today, so I don't want to take any credit for that, but just thank Bang again. And if you have any comments, questions about the center, I encourage you to have a look at the website or reach out to your local representative. There is a representative from each of the faculty that you can see on the website. I think that's all I'm going to say about the center today. So over to you again, Mang.
Yeah, thank you, Thomas. And from my own impression or understanding, I would like also to emphasize that AI for the People, it is aim to make the best out of the own activities we do at AAU and to harmonize the activity into the fit everything into a big picture that aim towards some meaningful goals for the people. Yeah, and Claudia also play a part in that. And yeah, I would like to present, and don't worry about the text. I have a challenge for myself and for you to go through this in 2 minutes and just give a very brief introduction. Okay. So the Claudia is user-centric full research lifecycle support. It focuses on you as the user, either students or researchers. And the team is now 3 infrastructure expert, 3 data management expert, 3 data science expert, 1 developer, and 1 team leaders that report to a steering committee from faculties. And the main category, or I would say verbs, that we do can be generalized into support of practical case issues, or give advice for the cases or the projects you have, or co-create with you, make solution, either software or hardware or a mix of both, or other research projects that we want us to be a part and collaborate, like internationally, internally, and across AAU, across national and international level. And we mainly can be divided into 3 areas: infrastructure, which you may have been using our GPU clouds or CPU cloud or the data deposit service. And there are also a server colocation service where you pay the money and then have us maintain and support the servers. And we also do hardware advisory for your project planning or funding, and also advisory on the compute resource outside of AAU. And for data management, we try to balance the stakeholder requirements. I mean, different requirements from different stakeholders, including the governing principle or organization like the GDPRs. All in all is to maximize the potentials of the project. And we do support, consulting, and guiding and training. And in data science, we do training for onboarding and technical, like to use the resource hardware, and also give course for PhD students, or also courses from the Deep Learning Institute. And the software engineering support, then we do troubleshooting for you when you have bugs or something you cannot run on the resource, or prototyping for you, so you can go further, like remove the entry barrier, and also do research support that give you from the left to right. You can see from a more kind of lighter level to deeper level of the project or research life cycles. And at the deepest level, we will be a part of your project and work with you as a member of project under this free scope agreement. And this, what we are doing here is very similar to the concept in business world they call cradle to cradle concept. In the old day, it was cradle to grave, but I think nowadays it's best better to be cradle to cradle. Yes. And the topics of today, the first one in the, I'm sorry, there will be one part that is Clement tell about NVIDIA and what it can offer for you with some interesting news or goodies.
Yes,
Yeah,
thank you,
please.
Fang.
Yeah.
So just before we get to the main event and having Nicola explain a bit more about AI and healthcare, I wanted to give you a brief overview about what NVIDIA can offer, specifically solutions and offerings in
Do
higher
you want
education and
to
research.
share the screen?
Yes.
Yep.
So.
I will stop sharing.
Yep.
And
Thank you. So there we go. Let me know when you can see my screen. Can you see my screen?
Yes, I can.
Can you see the big screen now?
Yep.
Okay, perfect. So just as a brief overview, if you don't know, NVIDIA, we started in the gaming industry. And since then, we have pioneered in the artificial intelligence and high performance computing verticals, creating the graphics processing units. So I wanted to just briefly talk to you about the higher education and research sphere. And then later on, Nicola will give you a kind of a more of a bigger overview with healthcare specifically, as this is the main topic this week. So first of all, just to kind of introduce myself, I'm Clémence Bigot, and I'm part of the higher education and research team here at NVIDIA. I believe that this is a really exciting time to be part of this overall community and this ecosystem. And we really believe at NVIDIA that we have the tools to help you both navigate through today, but also to prepare you for the future. So as a starting point, I just want to talk to you a bit about the challenges in higher education that I have and we have at NVIDIA observed, and just to see how we could respond to that and if this is relevant to you as well. So while this is an exciting time, as I said, there are some challenges that may impact the efforts that you're putting forth and that really do need to be considered. First of all, the battle for funding. As you know, more researchers are competing for level funding dollars, and IT budgets are not growing to match technology and infrastructure demands. Secondly, attracting best talent. Funds and lab equipment is a deciding factor for faculty and students as well. So changing curricula, there is a demand for skilled data scientists, as Vang put forward as well, and expertise, and it requires students to hit the ground running after graduation. And complexity, the research problems, the student projects, as you know, AI is advancing and HPC is becoming more complex than ever, and data sets and compute requirements are growing exponentially as well. And finally, in-person and remote learning, especially during this time. Distance learning at scale introduces a new set of challenges for educators, researchers, students, and IT staff, as you might be experiencing right now, especially during this pandemic. So just in general, the demand for AI is growing very fast. And I like to say the genie is out of the bottle with AI technologies, and there are multiple signs that show that the growth is accelerating. So the first sign would be if you see on the left, the number of papers that are published with AI, while the dark green line on the left-hand graph is showing the AI-specific papers doubling each year. The other important factor, that's the light green, is the use of AI as part of high performance computing or traditional science research, and that's also seeing a doubling. And there's been a number of papers year after year for the last 8 years, and that show that data science is impacting almost every industry. But deep learning is also playing a significant role in these industries, and you'll see later that deep learning in healthcare specifically as well is growing quite a bit. So with things like natural language processing and natural language understanding, those are a couple of examples. And then as well, you can see that the number of networks and the size of networks have exploded quickly with large networks such as GPT or BERT. So continually increasing the need for more and more computational power to be able to leverage these. So in this case, at NVIDIA, we want to address the challenges and the demands. So we want to, build by building a leadership, an AI leadership in higher education and research. So we talk to universities all over the world, and the 4 areas below really represent where we see leaders excelling. So first of all, we're all in this together. Think funding agencies, universities, faculty, and researchers, and even the industry partners, where the things that where the things have the way things have been done in the past are not going to address the leadership needs of today, particularly for universities, as you may have already experienced. So universities need to be thinking big about the current problems affecting their region or even the nation and the world. So you need to be prepared to find ways to fund at this level. And for example, the University of Florida, which I can talk a bit about more later if you're interested, has launched an initiative to holistically transform the university. Plus, universities need to understand what investments will be needed to maintain their top talent and the tools and infrastructures to do the research. And universities will also need to increase their research funding as a result of that. And we've seen multiple examples in the last couple of years. And finally, you need to find ways to accelerate building the AI expertise and skills that the industry needs. So how do you make sure that you're well connected into the needs that you're building for? That's where we come in, specifically for higher education and research. I just wanted to give you a bit of an overview of our different offerings. So we offer a wide array of hardware and software to meet all your needs. And Nicola will go into a bit more detail around that, specifically the software part towards the end of the presentation. But I did want to talk to you a bit about the fact that we have a track record in investing and partnering with universities over the last several years. So we have a very large developer focus, but we also have multiple higher education and research programs to support and accelerate a university in their computing journey. So that includes deployment of best practices based on workloads and university needs. As you can see, in the middle square here, we do offer teaching kits in the Deep Learning Institute, which I know Veng has talked about before, and that means that and a professor can get some free courses for the students to do, and that's very helpful in terms of training that to build the AI expertise. We also can organize some workshops or hackathons if needed for specific research groups. And one of the best things as well about higher education research is you do qualify to get an educational discount that I can approve for you if you wish to go through with procurement at a later stage if you do get funding. So for example, we have a big computing platform of which you can see that we have the new DGX A100 system, which I'm sure you've heard about. And that one you can get 30% off. So again, that's a really big benefit we give to universities because I feel like they would, they need to accelerate their research in the best way possible. And we know because of the battle for funding, we just wanted to help out a bit in that way. So just in terms of hardware, quickly, I just wanted to talk about the new MP architecture that we've brought out. And so the A100 specifically, it has 20 times more training power than the Volta architecture. And it can be used for inferencing, training, and analytics. And one of the biggest features of it is new as well. It's the multi-instance GPU, which means you can slice up the GPU into 7 different instances, and you can have 7 different people working on one GPU, which you couldn't do before. And with the DGX A100, which has 8 GPUs in it, you can have 56 people working on it at once. So again, that's a great little benefit there. And we have some new software that came out as well, we can scale up with the data center. So if you would like more in-depth technical discussion around our new hardware and software, for example, we do have some new Ampere cards coming out, one of which is a workstation card, then let me know. You can contact me and I can set up a one-on-one discussion with a computing solutions architect. I can leave it here, but would you like to learn a bit more about customer success stories that we've had over the last couple of years with some DGX systems? Or would you like me to leave that for a later time?
I think all in all, we have max until 2:30.
Mm-hmm.
That yeah. So and if that is okay with Rieke also, that Nicola, sorry.
I'm flexible, whatever you prefer.
Yeah. Okay. Yeah. So maybe a couple of minutes more to.
Yeah, of course.
Yeah.
That sounds good. So as I mentioned University of Florida before, I can start with that one. So the University of Florida announced a $70 million public-private partnership with NVIDIA that will provide students, faculty, and researchers access to the most powerful AI training and tools. So it includes 140 DGX A100 systems. That's about 700 petaflops of performance, which is a huge amount. And this partnership, it aims to create a framework to ensure equitable access to bringing AI to students and faculty from across campus and as well the state of Florida. And it will give faculty and students within and beyond the university the tools to apply AI across a multitude of areas to improve lives, bolster industry, and create economic growth across the state. So that's a great example for you to see. That is a very large scale example. So similar at KIT, there was a very large system that was installed recently with DGX and 100 systems. And you can read a bit more about that later on if you wish. But I'll just talk about one that is more of maybe a smaller scale. So we can talk about the Martineau Center for Biomedical Imaging, which they used. So they were working on MRIs and the fact that they can take up to 2 hours, and the subsample data can speed scanning time, but it contributes to inaccurate image reconstruction. So researchers at Harvard University and the Martineau Center, they're using deep learning to speed up image reconstruction without compromising accuracy, and their AI framework is powered by a DGX-1, which is currently not available anymore, but the DGX A100 has a better performance. So it's a great example to see that if this can be, they find that they have 100 times faster reconstruction and 5 times higher accuracy. Imagine what they could do with the DGX A100. So this is more of a smaller scale for you to have a look, an idea. And if you want to hear more about the different success stories, again, you can just drop me a note and I'm happy to help.
Yeah, thank you, Clemens. I think it also gives an idea of how others are using and investing into AI. And I can see that at AAU, we are also considering and also working seriously on bringing up AI more into research and also applications.
Definitely, yeah.
Yep. Yes, thank you. So I will move to the next part. I'm going to share my screen again. Where is the share button? Share screen. Yeah, can you see my screen now? Okay. Everyone can see my screen, okay? Hello?
Yes, we can.
Yeah, thank you.
Yeah, we can.
Yeah. Okay, and this is the main part. And okay, welcome. And I'm really excited that we make this far. And after, many discussion and to find out a way to bring this forward in this situation, we actually first wanted to make a physics a workshop where we can talk and discuss more easily. But now, yeah, this is our new normal. So yeah, let's do it. And thank you for coming. So the topic you already know, and I would like to say some words about our speaker, Nicola Rieke, and she is the senior solution architect from NVIDIA, and with a specific focus on deep learning in healthcare. And Rieke, throughout her career, has been working across three main areas, that is mathematics, medicine, and computer science. She is the active member of medical imaging research community. I mean, very active, and be also the pioneer in the research. And she got her PhD in the Technical University of Munich. And some years ago, I think she got the Young Scientist Award, the MICCAE Scientist, Young Scientist Award. And in the 2019, January, I was attending the workshop and also training to be the ambassador of the Deep Learning Institute. We met in Lausanne, Switzerland. And my impression that she is very good at presenting the materials and make it a really enjoyable workshop. And with that impression, I would like to give a very warm welcome to Nicola. Please.
Thanks for the nice introduction. So this feels like ages ago. So it seems like just 1.5 years ago. So it really feels way longer. The world has changed a bit since then, but I'm very, very happy to be here. Let me try to share my screen. Could you stop sharing? And then perfect. Then I'll go on with sharing my screen. Give me a second from the beginning. And this over here. Okay, so welcome everybody. It's a pleasure to be here. I would have loved to travel more north. So I'm actually based in Munich. So not that far away, but still traveling right now is a little bit tricky. So in the conversation, I know this workshop is not specifically about healthcare, and I won't make it specifically about healthcare. So we will have two main parts in this workshop. So the first part will be mainly around federated learning, which is a learning paradigm that is very generic. So my passion is with healthcare, so as Wang said, at the intersection of medicine, mathematics, and computer science. However, I think this learning paradigm is interesting to many of you because it's applicable for many different fields, because it addresses a very important topic. This is the problem of data sharing. So I will first go into this, and then in the second half, I will go a little bit into detail for software solutions for specifically deep learning in healthcare. So I guess there are a couple of participants that are interested in trying out new research or new development, new AI models in the healthcare field. So I wanted to highlight two different parts. So one is NVIDIA Clara, and the other one is MONAI. So we have 1.5 hours, so let me start, because we have a lot of content to cover. So as my colleague Clemens already said, NVIDIA has come far from the original gaming company. So now we are a computing platform company, and I'm part of the global healthcare team. So as I said, I'm based in Europe, but we are a global team and we all work together. So it's not only the GPU that we have, it's actually way, way more. So our core business or our core component is of course the GPU. So if you think about algorithms that you can accelerate, so everything at NVIDIA is about acceleration. So this is one of our major topics. And when you think about algorithms, every time where you have independent processes, whenever you can parallelize something, this is highly likely to be acceleratable on the GPU. So at the core of all of our engagements is this hardware that is one architecture across all the industries. However, and I like to say that, so that there is a secret to our success. So we don't stop at the hardware. our hardware only works so well because we accelerate across the full stack. And what do I mean with that? So you have the hardware, but at some point you have to talk to the hardware, right? So there are programmable parts in this hardware, and you can talk to them or have communication with them with CUDA. So CUDA is the lowest level of the communication, but we also don't stop there. We have CUDA libraries. So for example, if you work in AI, as we all do, you probably have used in TensorFlow or PyTorch or whatever you used at some point cuDNN, so the CUDA accelerated deep neural network. So this is just one of the libraries that we have in the CUDA-X, so the acceleration stack. And then we have several verticals that we focus on, but I won't go into more details. We have 5 industrial verticals that we consider very important and where we think that we can contribute a lot. So one is automotive driving, then we have robotics, for example. And here you see Clara Health. So whatever we develop regarding a software and hardware stack specifically for healthcare, we put it under the umbrella of Clara. So this will be covered in the second part of the talk, just to give you an impression where we are and where we stand. Okay, so what did we have so far? So we had the introduction to the entire workshop series, and we had an introduction about the technologies and overviews and use cases from NVIDIA. So let's go now to the second part, so about federated learning, which is collaborative learning without sharing data. In this case, patient data. So we'll explain a little bit with the example of healthcare, but always keep in mind that this is a very generic learning paradigm that you can apply for various different tasks. And as I said later on, NVIDIA, Clara, and MONAI. So why is federated learning so interesting for the healthcare field, and why does it fit so well in this workshop of AI for Good? So a lot of AI techniques, or one of the core component and requirement for a successful AI model is that you have data. So AI learns from data, and without data, you can't build a robust model that you develop for a specific task. So training of robust and accurate deep learning models require large and diverse data sets. And this led to a certain movement within research. So if you consider research papers, for example, in my community, in MICAI, so medical image computing and computer-assisted intervention, so this is MICAI, is one of the most important conferences in this field. And what we observed there is that research has made a lot of advances and has advanced a lot for the fields where you have huge data sets. So for brain tumor segmentation, there's, for example, the BRADS challenge, then you have endoscopic data sets, the Endovis challenge, and so on. So the research is really driven by data lakes. In situations where you don't have these huge data sets, you can't really apply the recent deep learning techniques, because the data, or a data set that really represents the underlying distribution, is one of the core requirements for many of these applications and many of these techniques. However, in the healthcare field, the health data is, of course, highly sensitive. It's patient data. It's subject to regulation. It cannot easily be shared. So even if I would like to work with you and you have a huge data set, you would not be necessarily able to share this data with me. So we really have to be careful of that because it's very sensitive data and we cannot share it directly. However, this is only one part of the problem. The other problem is that there are regulatory and legal challenges related to ethics and privacy, but also data protection, and technical ones. So if you consider healthcare data, this is particularly big. So we work a lot with 3D volumes, for example, or whole slide image in digital pathology. This data accumulates actually a lot. So it's not that easy to ship this across continents to centralize this in a data lake. So this is one of the problems, and this leads sometimes to a situation where there's huge data sets actually have a demographic bias. So if a data set is collected, for example, in London, it might represent the London population, but not necessarily a patient from China. So this is one of the problems. And on the other hand, is hindered research. So for some diseases, luckily the diseases are not that common. However, this also means that you don't have this huge data sets in one single institution, and centralizing this data set is very, very difficult. So here we really have a problem, because there are many research areas in healthcare that we simply can't address right now with deep learning, because we don't have this huge data sets in one location. So we really rely on the data to create robust models and actually have large scale training. So just sharing the data set, as I said, to a centralized location is not easily possible. So what can we do if we, as a single institution, can't contribute our data set to centralized location even if you want to? Well, let's just invert the idea, and instead of centralizing the data set to train the model there, let's bring the model to the local institutions and train there. So instead of sending the data to a centralized location, we send the model that we all want to train to the local institution. So federated effort or federated learning is collaborative learning. We all work together, or several institutions work together, without actually sharing the underlying data set. So without sharing the patient data, without having the patient data actually leaving the institution. So it works in the way that you have a consortium, so you have a federation, and you decide on a specific task that you want to train on. And you decide on the model. This model is like the same for all of them. Then at some point it's sent down to the local institutions, trained there a little bit, and sent back to share the updates. So I will go into more detail in a couple of slides of that. However, to already keep in mind, one important point right at this point is you never ever share the data set. So you only share your learnings. And your learnings in this part are the model updates. So let's assume you are a hospital and you have some computer resources, you have a model, and you have a little bit of data. However, this data that you have is not sufficient to train a robust AI model. So you are in contact with a different hospital or a different health institution, and they also want to work on this task. They also would like to work on a model. They have a completely different data set. So bigger, smaller, completely different bias. So it would be interesting to combine this data set to have a more complete data set for this AI task. However, they are not allowed to share the data, so they want to collaborate. So in this scenario, federated learning can make sense because it allows algorithms in general, not only deep learning algorithms, to learn from non-collocated data. So I guess, so in this workshop, you're all familiar with AI and AI training. So I won't go into a lot of detail here, but just to grasp the concept. So the first AI algorithms, like now 5-6 years ago, they really had this boom. So they were older, but 5-6 years ago, there was a big wave of AI. So the traditional AI training, you had a huge data set that you had to curate, you had to label, that you have to train, and so on. So it requires a huge data set. It requires a lot of compute at one location, and you train a model there in an iterative process. Okay, so this was the original or traditional AI model, AI training. Then for a different field, so in particular for healthcare, we not always have this huge data sets. However, at some point, we discovered transfer learning. So what you can do is, instead of training a model from scratch, you can use a pre-trained model. So for example, from NGC. You can use this model and use this as a slightly converged model. So you don't start from scratch, you start from different numbers, and this allows you to have to work on less data. So you just fine tune on your local data set. So you still have local training, but you adapt to an external model. So you use external knowledge and you bring in your local data set. If you think about this one step further, so what if this external model doesn't really exist and your data set locally is way, way smaller? what do you do then? So then it goes into the direction of federated learning. So see here, if you consider this loop, it's actually very similar to here. So locally, the same AI process happens as always. So you have your local data set, you have a model that you train, the PyTorch, TensorFlow, whatever. This local loop stays the same. However, this global model that you use is not a fixed model. However, this global model you develop together with other participants. So you still have this local training, but you collaborate on a global model. Okay, so in some way, it's still transfer learning, however, without a fixed model externally. And the other point is that you don't train until convergence, so only a couple of iterations locally, and then you actually send back the model updates to either to the others or to a server. So you combine the learnings that you had locally. So just as a timeline where to put federated learning. So why is federated learning then interesting? So as I said, federated learning is a learning paradigm. So it's a technique and method how to train, in which multiple parties train together without centralizing the data set. So it's interesting because it neatly addresses the privacy and governance challenges. So by not exposing the patient data, you sidestep this complication of the entire AI training process. And by doing this, it could actually create new opportunities. So it could allow new research directions, for example, rare diseases where you can't collect the data. And another part is that medical data, for example, is duplicated, and it also allows for additional privacy protection. So by construction, it already gives a kind of privacy component because you don't expose the data set. However, you can even enhance this by additional measures, as I will explain in a couple of slides. So what is the impact of federated learning? Just considering from the healthcare perspective. So it increases the value of AI for nearly all healthcare stakeholders. So starting from clinicians, of course, clinicians are interested in robust models that they can actually trust. So the bigger or the more representative the data set the model was trained on, the more robust it gets. So it can also include patients in remote areas, for example. Researchers get access to large data sets without requiring it to be centralized. So new research direction could be opened. It's interesting for hospital and practices because, for example, even though they don't have their own data scientist team in-house, they could make the data that they have in-house, that could make it available for new research direction to researchers and enable new research direction in this. And of course, it's also interesting for manufacturers. So as I said, federated learning is collaborative learning without sharing the underlying data set. It's very vague, and it's on purpose very vague because there are a lot of flavors of federated learning. However, if you want to define it in a certain way, like at least a bit, so broadly speaking, it can be defined as collaboratively working on an optimization function. So you have a global loss function. Let's say you have a segmentation task, and then the global loss function is a weighted combination of the local losses. And the local losses are always computed on the private data xk. So here, this data is local and is never shared. So globally, the entire global model minimizes this global loss function, which is a combination of the local loss functions of the participants. And two main characteristics for federated learning: data sets are distributed and you work on a shared model. And there are many ways of how to create such a federated learning workflow. One of the most common one is the client-server approach with an aggregation server. So it's, again, an iterative process, as you always have in AI. So you start, in this process, you have two main players. So one is the server and the other one are the clients. So the clients have the data. On the first step, the server distributes the global model to the local clients. They train with the local data. They send back the model updates to the server, and here it's aggregated. However, you can also imagine, so there are also approaches where you actually don't rely on the central server. You can also have a peer-to-peer approach. So you start with a model. This is sent by one of the participants to all the other participants. They train on the local data, and then they exchange the models automatically, so directly to either the entire consortium or just part of that, and the aggregation happens locally. So they all work together, and they work on a model together, either on the entire model or just part of the model. And yeah, so there are different architectures. I won't go into detail because otherwise we're running out of time. But if you're interested in that, I would recommend this publication, the recent one, where we brought together thought leaders of this field for federated learning in healthcare, and we investigated different, like the benefits and the impact of federated learning for medical applications, as well as key consideration and challenges of implementing federated learning. So healthcare is very different than normal computer vision tasks, for example. Let's go just through a very common or like a usual federated learning round. So let's say you have 3 hospitals that want to work together, and as it's indicated here, they all have different local data, so the data set size might vary. However, they all have local data and they all have local compute. So in the first iteration, they decide, okay, we want to work together on something. They decide on which task, and they decide on the global model. Then the server actually sends down the model to the local institutions. They train on the local data. Then they have a local model. So this local model is then sent back to the server, either the entire model or just the delta, so the difference between the global model and the local one, or the gradients, or there are different approaches. But in the end, you share your learnings that you had locally from the couple of local iterations. And the federated server actually collects all this information and combines it to a global update of the global model. And then in the next iteration, you send it back to the local institutions. Now, federated learning addresses the challenge of data access and data governance. So at any point, the institution can say, okay, I'm out, I don't want to participate anymore. And throughout the entire process, the data remains in their possession. So they can decide at any point to join or disjoin the federation. However, federated learning does not solve all the problems. So as you might be aware, the deep neural networks implicitly have some information of the data sets that they're trained on. So if you really have a potent and a really good neural network, you can actually reconstruct some of the private data. So even though you don't share the the local data and you just share the model updates, there is a risk that you can reconstruct some of the original data. So this is a very common and issue with deep learning. However, in federated learning, you can actually enhance this privacy component by adding a privacy preserving measure. So imagine instead of sharing the very clean model update with the server, you just share part of it. So imagine you have a matrix of 10 by 10, let's say 10 by 10. You could randomly mask some of these values just by 0. So just 0 some of the numbers, and then you already have a very different information. Or what you can do is put Gaussian noise on the numbers. So instead of 1, you share 0.9 or 1.1. So in this scenario, it becomes way harder to actually reconstruct the original information, and then it's even harder to reconstruct the local data. So federated learning enables to add this additional privacy preserving components. And the nice part is that even though you don't have the centralized data set, you can reach the same accuracy. So this is one example. So this is from MONAI 2019, I think, from one of my colleagues. So he investigated federated learning for brain tumor segmentation and added a privacy component on that. So here in orange, you see the accuracy in terms of dice score on the validation set. So it's held out, it was not seen during training. And you see for the first couple of epochs, actually the data centralized training is way better than federated learning. And in the end, you give way more and clearer information at the beginning, so it's clear. However, the federated learning, federated averaging, so one of the very common techniques for the aggregation, actually converges to the same value as it does for data centralized training. So what we see is actually this opening up of the training iterations for several institutions enables you to have the same accuracy without centralizing the data set. And I don't know if I have the slide here, no, but he actually investigated how much information do I actually have to share in a clear way. So how much privacy preserving measures can I add and the model still converges, and it was quite impressive. So I won't lie here now what the exact number is, but I think it was, even if you only share 50% of the model updates, it still converges. So it's quite nice. So some technical considerations that you have to take into account in this entire part. So as I said, privacy and security. Federated learning addresses some of the issues of current AI training issues. However, it does not solve all of them. So yes, the data sets remain locally, but some of the attacks, like adversarial attacks, can also be applied here. One of the directions there is to add privacy preserving techniques for federated learning. Just one of the examples. So there's way others also. And depending on the federated learning consortium, you might want to add different ones. So if you are really in a trust and you have a legal agreement, then you probably don't have participants with bad intentions. So then you can also think about adding less privacy preserving measures. One of the major problems in this field, not specifically for federated learning, but in general, is data heterogeneity. So medical data is particularly diverse. So you have 2D, 3D, 4D, 4D plus T. So there are different types, different like ultrasound, MRI, CT, and so on. So it's not as easy as the applications that you have on the phone, for example. So one of the core requirements for AI is that you have certain standards before you train, right? So you have to create your data set in a way that it's digestible by your AI training, and this remains the same in this setup. However, it adds another complication because the participants can't look on the data sets of the others. So this is one of the core characteristics of federated learning, which is a good thing, but also a bad thing, because if something does not work right in your AI training, usually look at the data sets or the cases where it does not work. So this is not possible in the federated learning setup. And one of the requirements of federated learning is that the data is independent and identically distributed across participants. So this is nearly never given in healthcare situations. However, recent research has shown that it still converges, so there are a couple of measures that you can apply. And one part which is very important for healthcare is that the global solution may not be the optimal local solution. So you have to think about what you actually want. So if you are thinking, for example, in automotive driving, across the globe, there are very similar concepts. So you have a street, you have street signs, you have speed limits, and so on. However, a global model can't necessarily always work for the local situations. So you can work on the global model altogether, but then you might have to fine-tune it still on the local data set. So for example, street signs are very different in Germany than in US, for example. So the sign with no speed limit is probably not existent there. Another part is traceability and accountability. So if you work together on a model, you may want to trace which participant actually contributed how much, because this could either introduce a bias in the data set, or you want to have it monitorized at some point, for example. So having a traceability and accountability in this situation would be beneficial. And one important point that I wanted to address is the system architecture. So for example, in this situation of healthcare, usually you have very different requirements than if you have on the edge devices. So usually a hospital does not move that far. So usually it stays at the same spot, and usually should have stable network connection and has way more compute resources than if you go to edge devices. So this has to be taken into consideration regarding the learning rate and everything. Some of the consortiums or collaborations that we work on federated learning, just to mention a few. So for example, with King's College London and Auckland, we work on federated learning for healthcare, so medical imaging applications in the King's College Trust. So several institutions together, several thousand of patients, patient data where we can actually combine these via federated learning. The other example is, for example, Farmer. So the Melody project where we are involved in addresses rather the discovery of new drugs. And this is super interesting because there are actually participants or partners that are actually competitors. So they work together towards the same goal without exposing their internal knowledge or IP. So federated learning can also enable to work together even if you are competing industries. So I will, in the second part of the talk, I will address the Clara federated learning, which is an implementation of federated learning for research and development purposes. So it addresses the communication setup in a federated learning setup. So, but I will go into more detail later on. Just a little bit of background in federated learning healthcare. So it got a lot of traction. So we had our first international workshop at MONAI for distributed and collaborative learning 3 weeks ago, I think. So it's the first of its kind in the community, and we had a lot of submissions. So it becomes a more and more important topic. So if you're interested in this field and want to do research in this field, it's a hot topic. I would encourage you to look into this direction. There are a couple of open federated learning research questions that we also try to address, but there's a lot to do. So if this topic is interesting for you, I would encourage you to try it out. One of our recent real-world implementations in terms of research was for COVID. So this is an example where it's highly unlikely that you can centralize a data set that is sufficient for AI model training. So luckily, the hospitals locally don't have enough cases that would allow them to train an AI model locally. However, we have a lot of cases globally. So it's unlikely that Asian hospitals can share their patient data with European hospitals. However, with federated learning, we can work all together. So this model that we trained recently and announced at GTC, so our GPO technology conference, is an AI model that predicts the oxygen need of a patient. So it's not for the diagnosis of COVID. You would simply do this with a test. However, based on the chest X-ray and some medical data, it predicts if this patient will need to go to intensive care or can stay at home, or which kind of oxygen support it will the patient will need. And in this scenario, we worked together with 20 different sites across the world on this model, and actually showed that it improved for every single institution compared to a model that would only be trained on the local data. So a real world implementation that hopefully actually helps in a real world scenario. And let me look on the time. Just to give you a feeling for the numbers. So this is another experiment that we did on real world data, different application areas. So this is regarding breast density, was an experiment that we did a couple of months ago. So it was a research project where we tried to estimate the breast density because it's a significant risk for breast cancer. And the data is actually mammograms, so the images of the female breast. So mammograms actually have very diverse contrast and appearances. So it's definitely not IID, so identical distributed. And there's even very inconsistency regarding the radiologist who looks at the images. However, so here is actually what I wanted to show. So this is, you see the intensity distribution of the mammograms of the different institutions. So here, institution 1, you see it rather on a bright spectrum. Then you have different institution 2 here is in the middle. And for data preparation, we asked the physicians, well, shouldn't we normalize the images and make it easier, because IID is one of the core requirements for federated learning? And they said, no, it's not possible because actually the intensity distribution gives you an important hint for the density or not. So we left it at the original intensity distribution and tried the federated learning. And actually it showed that there was an improvement in the AI model across the board. So here you see institution 1. So this is trained the model that was trained on the data of institution 1, applied on the institution 1, and of course it performs best. And if you would take this model of institution 1 and apply it to the data of institution 2, it performs worse. And actually here you really see that this model or this data that you have here is not representative of the data that you would see in institution 3 and 4. So if you take this model and apply it here, it won't work. So you really have low accuracy here, and even worse here. So in this scenario. However, if you would take the entire data and have it centrally hosted, the results improve a lot. So then this model applied to the various different institutions actually perform well. So this is this is what you would need for training an AI, like a robust AI model. However, as I said, it's not always possible. So in terms of federated learning, then you do the same, but you leave the data locally at the institution. And what's nicely seen here, it actually improved for all across the institution. So you even without sharing the patient data, you can create a robust AI model for the participants. Okay, I will stop here and see if you're still there because I talked a lot. Maybe I open it up now for 10 minutes, 15 minutes discussion around if there are any questions regarding federated learning, because we will move to a different topic afterwards.
That's a good idea. I think please, if you want to ask a question, I think to maybe just type your name. Yeah, someone put an X on the chat box. Yeah, then we will take a turn and pick up the question. There is the first question there. So if you want to type the whole questions, then type in, or you just type an X or anything, just take your place in the queue, and then we will pick up. Yeah, the first question is from Afsan's Money. I don't know, is that a full name? But he said, I wonder how the overall loss function be minimized with having access only to the weights without inputs and output of the model. Mm-hmm.
So good question. So a tricky question. So the loss function is actually defined in the federated learning protocol. So you define the overall task, what you want to achieve, like the model that you want to train, with which objective. However, the training on the data actually is done locally. So the loss function is actually performed locally at every single participant. So there you actually have the input and output, and you can actually, you optimize the model locally for a couple of iterations, right? So in this moment, you actually need the loss function. What happens in a server-client approach, for example, at the server then, once you send up the model updates, you just combine them. So let me see if I can go to the slide. This one here. So this is actually the federated average. So you don't look for a loss function here in the server. What you actually do is a combination of the model updates that are based on the optimization of the loss function locally, and you just combine them. And you could just do a normal average if you want to. However, what is more common is a federated average, which normalizes the contribution based on the size of the data set locally. So in the end, it's just a aggregation of all the information without optimizing, and then this is the global update of the model. So average of weightings, yes. Smart average. So you could average them just like this. However, then you really have to have IID data. More common is the federated average, which is normalized to the size of the local data set. However, there are many different ways of how to aggregate. So it's called the aggregation step, how you combine the information.
Yeah, thank you. Next is Tobias.
Hi.
One of my colleagues. Yeah.
Hi. Thank you for the presentation. I got a little curious about one of the figures you had. I think maybe it's the next one or next one again. Help you. This one actually.
Mm-hmm.
Oh, yeah. It's just when it's just for like imagine that you set up a federated setup, and then you got the green curve in this case.
Mm-hmm.
How would you assess if that is good enough without knowing the, yeah, what kind of measures would you put in?
So you are indicating you don't know the difference between the green and the orange one because you don't have the orange one in a real setup, right?
Yeah, that was yeah, exactly.
Yes, so for research papers, you can show the difference. So that's a nice thing. So you can really investigate if your contribution, like your new aggregation method, your new technique, whatever, actually performs as if it would be a centralized data set. So in this scenario, in this synthetic setup, you can see the difference. In a real setup, so where we did, for example, the COVID data model, it's not possible. So here you can't say if this performed as good as the model that would be trained on a centralized data set. What you can always compare is the federated learning, federated model compared to the local models. So models that are only trained on the local data. So this difference you can always see. And what we did here was actually, it's a little bit tricky because sometimes the the model learned in a federated way performs actually worse than the model that you would have locally, simply because of the reason that you overfit to the local data. So what we did was continuously checking on the validation data locally how the model performed. So you can share the information, right? So this is nothing regarding data, the local patient data is just the validation accuracy locally. So this you can do, but there's no way, as far as I know, to actually estimate the difference between a model that is learned in a federated way compared to the model that is learned on a centralized data set without having the centralized data set.
Yeah. So there's a comment from Afsan Mani. I assume federated learning should be suboptimal to compile a data set training as shown in the curve, but the example on the X-ray was opposite.
I think you mean mammography, right?
Yeah.
So I don't know where it is right now. Yeah. So in general, we would expect that the federated, the model that is learned in a federated way is always, in the best case, as good as if you would train it on a centralized data set. So this is a goal that the golden goal that you want to achieve. However, there's always a random factor in AI training, right? So why do we use stochastic gradient descent? We could also, if you have enough compute power and the model is small enough, we could also do a gradient descent on the entire data set. So the random factor is actually an important component of AI training. So I don't have a mathematical exact reason here right now, because I don't want to claim something that I don't know. But in the discussion with these researchers, we think that it's due to a random factor in this AI training. So seeing a subset and optimizing iteratively on small batch sizes can have another outcome, as you have a batch size that would include the entire data set, right? So this is something what would be what happened here probably. However, I don't think that this difference is statistically significant, really. So I would rather say it falls into the category of performing as well.
Thank you. There's our next one from Thijs. Is the validation data shared, or how is it calculated?
Good question. So there are different approaches. And the normal federated learning setup, you don't share any data. So also the local data set is has the normal splitting of training, testing, and validation. So what you share is not the validation data, but just the result of executing the model learned in a federated way on the local validation set, and then just report the results. However, there are also research approaches that say, okay, what if we share part of the model? So what if we have a representative validation set in the server and we can do the validation directly there? So in this case, it's not a very clean federated learning, because you still share clean data, like the raw data, but there are approaches that also look into this direction.
Thank you.
I hope this
yeah. I would like to also put in one burning question I have been waiting, and also other. I think we have a couple of minutes more. Just from the Claudia point of view, we want to support researcher if they want to do federated learning. Actually, we have a project that is very good case of federated learning. So I mean, when things work, it's very nice. But before going to arriving to that point, what is the preparation and also setup in terms of infrastructure, and what the researcher need to be prepared in order to use this paradigm?
Yes. So federated learning does not solve all the challenges that we have with AI training. So some of the components remain the same. So defining the task, defining the model, preparing the data. So especially the data preparation is not solved by federated learning. So if you have a couple of researchers that want to work together on a federated learning models, they have to define the tasks that they want to work on. They have to define the standard that they want to use. So if it's a segmentation, one easy example is the label going to be 1 or 0? So even that, like, this standard has to be the same, and it's super complicated because you can't look on the data set of the other researchers. So you really have to have this fixed in the federated learning protocol and say, okay, I want to have this model, these are my kind of labels, I want to train in this way. So this has to be done anyway. So this for all the AI training, right? The part that you have to do for federated learning is that every single participant has to have local compute.
Mm.
So if you work together with other institutions, for example, hopefully they also have a nice DGX cluster. So then you can work together. However, federated learning does not require that you have locally the same compute. You can also work with DGX2 and DGX A100 or other cards. It does not even have to be DGX. So local compute so this is one of the requirements. And what is complicated is this communication. So if I go back, where's the slide? Maybe this here. So if you implement it by hand, this communication and this synchronization actually here is a little bit cumbersome. So you have to decide, when is the model sent to the other participants? When is it sent back? When is it aggregated? Do we actually wait for all the contributions, or what happens if this participant actually drops out because their network connecting issues? Do the others have to wait until this guy is up again? So the entire communication process is a little bit complicated, but we do have a solution for you if you want to do that. So Clara Federated Learning takes care of that, for example. So it takes away this communication issue and allows you to focus on the important parts of what you're interested on. So the research and innovation.
Yeah, thank you. That gives some ideas.
One question from my side that I would have, because this is a very not only healthcare group, right? So this is AI for good. So where would you see federated learning be applied in your field? So do you see their potential? I'm curious about that.
I would like to give that to our attendees, researchers, to give some ideas. Please go ahead.
Be brave and unmute yourself. No potential at all? That's sad. I can think about a lot of things.
Someone turn on the camera, yeah.
Can I talk?
Yes, please.
Yes,
Peter.
so I'm Peter. I'm at the computer science department. I'm working on recommender systems, a little bit on transfer learning, and obviously it's about users. So I believe there is a potential in federated learning for preference learning, user preference learning.
Mm-hmm.
I guess it overlaps a little bit with healthcare as well, because there it's the user data and privacy. So it's I would have to think about it, but I think there is a potential for that.
Mm-hmm. A very good point, actually. Without saying company names, on your phone, actually federated learning happens today. So Google is very so they are very strong in federated learning, and whenever you have your phone connected to on power and you have Wi-Fi, they actually do federated learning to protect your data, to not soak your data to their server, but still improve the AI models on your. So whenever your phone gets a little bit warm and cozy, they do federated learning on your devices. So it's not. So federated learning is coming, so it's not just a dream, it's actually already there, different fields. But I totally agree on edge devices, and it's really, really important, because you don't want your data to end up somewhere, right?
Yeah, but there is always this problem, like how we are going to test those models, and I'm not sure we are going to solve it very easily, because if the ground truth is not there, so how do we know that well, of course, for Google, Amazon, Facebook, LinkedIn, and so on, the data silos, they own the data, right? So for them, it's, I mean, they have signals and they own them. I mean, even when they don't see that much from my mobile phone, where they see enough. They see my weblogs, where they see my activities anyways. So I believe for them it's possible to evaluate and they work on that. But for us researchers, I don't know. I mean, it's just tough. I'm not sure how one can do that.
Well, I'm not 100% sure what you mean with ground truth. So are you referring that you don't have the centralized data set to compare to?
Yeah, so the labels, basically the labels you evaluate against, if it is supervised learning, right? So so if you don't have true labels, if you don't share them, then, and they are usually in the data set in our domain. So it's like either rating or some other signals, buying history or whatever. I mean, it's so they are in the data set if you just learn it from the data set directly. If in pure federated learning you don't share these labels, then
So federated learning can be combined with supervised learning. So this is what we were working on. However, there's also federated reinforcement, for example. There's also federated unsupervised learning. So so the label, so federated learning opens up the AI training iteration cycle. That's what it does. So instead of having this all happening in one place, it happens in several places. However, it's not restricted to supervised learning. You can combine it with any other learning paradigm that you want to.
Okay.
But you're right. So the big companies have an advantage there. So.
Yeah, as always, and as with everything, right? They have money. Well, you have money too, right?
Well, but we are not a data collecting company, not at all. Okay. We don't collect data in no way. So, for example, in this case, also in the COVID case, the local institutions automatically had the data in the way that they had the X-ray. So this is a data that you usually collect when you have a patient that goes to the hospital. So the labels in this case were given by the medical health record. But every institution these institutions did not have a sufficient data set to train an AI model, but altogether they're strong enough and have a representative data set where you can actually train a model. So I would rather think in this direction, where federated learning could be a benefit for you AI training is possible, however, you lack the size of the data set. So in this direction, it can help.
I think it's almost 3:30 now, so
yes.
Let's move on to the next part.
Okay.
And, yeah, I saw a comment or question from Mohammed, but sorry, we need to move on, and then
yeah. Also because I have a hard stop at 4, so I have to move to the next meeting. So let's maybe continue a little bit with NVIDIA, Clara, and MONAI.
Yeah.
I will rush a little bit through the slides because not everybody might be interested in healthcare solutions. So maybe we can still have 5-10 minutes at the end for discussion, maybe.
Yeah.
So now it's 3:30, right?
Yeah.
Okay, let me bring the chat over here so that I actually see my slides. Okay, so we started with the workshop overview in general, then in NVIDIA in general, now a little bit more in federated learning. And I would encourage you to think about, as I said, areas where federated learning could enhance your AI development, so where it actually would be a nice fit. I think there's a lot of potential. Happy to discuss this also via email or a different discussion. So the last 20-30 minutes, I will rush a little bit through NVIDIA, Clara, and MONAI, which are software toolkits for deep learning in healthcare. And I will start with Clara because if you are starting with federated learning, it has the federated learning component that you can simply use. So it is a software toolkit for healthcare. However, it can also be used agnostic to other kind of data. So if you want to experiment a little bit with that, feel free to do that. So it does not recognize if this image is actually an X-ray image or a different JPEG. So maybe it's still interesting also for the other groups. Let me around. So NVIDIA Clara. So as I said in one of the first slides, we have several verticals where we think that we can contribute a lot. So and that we consider super important. One of this is healthcare, and everything that we have in terms of healthcare solution we put in the Clara umbrella. So it's NVIDIA Clara application framework, which is a domain specific to accelerate the development and deployment of healthcare applications. So this is a very oversimplified view, but I hope it gives you the impression of what it actually contains. It actually started with radiology. So this is the lung here, but by now we also have the genomics part and smart hospitals. So the medical imaging part is called NVIDIA Clara Medical Imaging. The genomics part is called NVIDIA Clara Parabricks, and for smart hospitals, it's NVIDIA Clara Guardian. And the idea here is to accelerate the development and deployment of healthcare applications in general and AI applications in particular. So if you consider the development of imaging AI models in the healthcare domain, similar to other domains, you first have to start with data. And data in our field is super, super tricky because you all know that supervised learning is one of the most common learning paradigms in AI training. However, the labels that we need for healthcare have to be done usually by the physician, by the experts. And if you have ever tried to talk to a radiologist and ask them, well, could you sit next to me for 1 hour and label this data for me? They would probably have said, yes, happy to, but I don't have the time because I have a patient here and I consider the patient more important. So we rely on experts to actually create the labels, and we have to annotate them. So one of the core difficulties in healthcare AI development is to speed up the annotation process. So the NVIDIA Clara Imaging has pre-trained models that can be used for that. So either directly for transfer learning, so you can skip this part and go directly to the training framework, or AI-assisted annotation. So you can use these pre-trained models to accelerate the annotation process, since it's 10x speed up or more or less, depending on the task. But this is one of the components that we try to accelerate with Clara Imaging. Then the major focus is on the training framework. So actually how to accelerate the training itself, how to enable advanced training capabilities. And then at some point, you also want to deploy the solutions, right? So this is a completely different task. So that's why you also have it in a different bucket. So the overview of NVIDIA Clara Imaging is we address the development stage. So everything that you need for the development of an AI application is in the Clara train component. This includes pre-trained models from various different organs, modalities, and so on. They usually originate from our healthcare research team, so they are participating actively in research competitions, on research projects, and usually whatever they develop, we try to make it available for you. So you can simply use that. So either for this AA is AI assisted annotation. So you can use these models to give to give first segmentation, for example, and then you only have to correct this. So in this way, it's already accelerated the annotation. But it also includes smart annotation tools like a smart polygon and so on. More interesting probably is the training part. So we have a training framework that currently is based on TensorFlow. So it's not a re-implementation of TensorFlow. It's a wrap around that allows you to have training in a very standardized way. And because it's so standardized, it allows nicely advanced features like AutoML, federated learning, and so on. I will go a little bit more detail on that. And for the deployment stage, you usually don't work on your model anymore. You actually have the problem that you have so many models that compete for the same resources. So it's rather about orchestration, scheduling, monitoring, and so on. So this is the deployment stage to actually use the models, AI models, but also other algorithms in your healthcare environment. So if we look at the general overview of Clara Train, similar to other core concepts, we don't care which hardware you're using. So it should run on our most common GPUs or recent architectures. Has two main features or capabilities. So one is the target is to create AI-ready data. So this includes pre-trained models, interactive annotation, AI-assisted annotation, and so on. And the second part is the training framework. So for now, it's a tensor-based training framework. We will soon also move to PyTorch. It has configurable MMAR, so medical model archive and pre-trained models. I will explain in a second what it is, and allows by having this structure to have this more advanced features like federated learning or AutoML. So just as a side remark, we don't try to replace any current solutions. We try to bring the components where we think that we can contribute. So for example, we don't try to invent a new medical viewer. There are many great solutions out there like MITK, 3D Slicer, Fovea, or OHIF. And we rather focus on the component, how to bring computational expensive parts to this viewer, so to make this faster and more accessible. So for example, this AI-assisted annotation server, we integrated in MITK and 3D Slicer and all the different components. So you can simply use it there. I won't talk more about this creating AI-ready data because it's probably not your most important topic, especially if you work in different domains. So I would spend more time on the training framework actually itself. So maybe I should show you this directly. I'm not sharing my screen. Let me stop sharing and let me share my screen itself. So in the end, Clara is nothing else than a Docker container. So if you go to NGC, that you probably also have available in your cluster. So here I'm just a guest. If you go to containers and just click for Clara, you get a lot of options. So the training part is called Clara Train SDK, as I said. And then you see the current version and you can simply pull it. So here you can also see Docker pull. You can simply use that. And you see here the links to the most important documentation and so on. So also an AWS quick start if you don't have access to the cluster there. And so Clara Train in the end is a Docker container and has everything ready for you there. For example, so it works with MMAR. Let me quickly show you this too, so that you get a feeling what it is. So MMAR, so this is one example of MMAR, so medical model archive. And if I go to file browser, what it is, it's a file folder structure. So here you see it's a zip file, and when you unzip it, you actually end up with this folder structure. And this folder structure is necessary for training with the Clara train framework. So it has commands, config, docs, eval, models, and resources. So if you go on models, for example, you see this, the model or the backend of Clara is actually a TensorFlow. So this model is saved in TensorFlow format, and you can directly use it here. The other important folders are the configuration files. So how Clara works is not that you open your favorite editor and start working there, so import Clara or something like this. It rather works with configuration files. So for example, I think I can't open it here. No, I will show you in the slide presentation, but in this configuration files, you configure, you set all the important parts that are necessary for the training. So where is the data set? How should the data sets be split? Which transformations do I want to use? Which metric do I want to use? What, and so on. So all the different components are actually in here. You set everything up, and then you can use the commands to actually kick off the training. So this is the train.sh, for example. So let me go back to the presentation, which is this one, I think. And why did you move up there again? Sorry for that. So here you see an MMR, so medical model archive. So it's a data organization or folder organization. So in the environment file here, so environment JSON file, for example, you just say where your data is located. You say, okay, in this JSON file, I specify how it's going to be split. So for training, I want to use this images and this labels, and for validation, this images and this labels, and so on. Then you point to the folder where you have the model, and in the end, everything that you need to specify what for an AI training. Then in the configuration train file, for example, you can say, I want to train for 1,250 epochs with this learning rate. In this case, I don't want to use a multi-GPU. And then you can simply say, I want to use this loss function optimizer and so on. So you don't specify everything in a Python file. You just specify everything in a JSON file just by writing them out. And we have a lot of transforms already available. Very specific to medical imaging, however, also applicable for other fields. So usually you compile your pipeline like step by step. So you load the file, then you transform it to an array, you scale the intensity range and so on. So you can just create your pipeline there in a very easy way. Same for models. So you just have to say which models you want to use with the different arguments. And there are a couple of models that are already there. However, even though we have a lot of transformations and models, probably it doesn't 100% fit your use case. So in all these parts, you can also bring your own components. So you can bring your own model, you can bring your own transformations, you can bring your own loss function, you can bring your own everything. So in the moment where you bring your own component, you have to implement it right now in TensorFlow. So simple TensorFlow model, and you can, if you have a certain structure, you can just say that here, name my own model, and it will use the right model for that. So you can bring your own component, but bring it in the way that it's standardized as given in this example. Once you have set up everything for the model training, you can kick off the model training with train.sh, for example. And you see here, you could also type this in your terminal. It's just it's a script that simplifies your training. But in the end, if you want to use it, if you want to write it yourself, you can also do that. The nice part is because you have set up everything in the JSON file, you don't have to configure anything else here. It's a quite nice way. So why did we create this Clara train? So it's not, as I said, not to replace TensorFlow or PyTorch, but to bring in our knowledge of GPU and medical specific operations. So the intention of Clara is to be GPU optimized, include automatic mix precision, determinisms. For example, this is also interesting for the V100s that you have in the DGX in your cluster. We tried to optimize the I/O processing, so bringing the data as fast as possible to the GPU and having it as scalable as possible. So in the moment where you really structure everything in this very standardized way, the scaling out becomes way easier. And just so this slide is already a little bit old, so it's a couple of months old. Probably the numbers are different now. We had another release in the meantime. However, I hope it gives you an impression of where we're going, what we're doing. So as I said, Clara as a backend has TensorFlow. So this is an example of a very common neural network architecture. It's the UNet 3D, which as UNet is nearly used for all the use cases in the medical field. And it uses spleen data sets, so it's a challenge from MONAI. So it's a 3D model that is trained, for example, on one GPU, and with TensorFlow native, it took 30.9 hours, like beginning of this year, to actually train it under convergence. With Clara 1.0, which was like a previous release, we gained roughly half an hour, not that impressive. However, we worked a lot, and with the newer release, we have another one already, but with this in-between release, we actually speeded up quite significantly. Not by changing the model, not by changing the code itself, simply by bringing in our GPU knowledge. So simply by bringing in automatic mix position, smart cache, and the imaging pipeline, we brought it down to 43 minutes. So instead of waiting more than an entire working day for the results, you can actually kick off a training every single hour and see the results, which is quite impressive. Quite nice. And of course you can scale it up to several GPUs. So if you ask nicely and get several V100s on your cluster, you can actually have the results in 8 minutes. So several experiments in them in an hour. So that's why we do Clara Train, to really accelerate the AI process significantly. So just as an example, I hope you already tried out automated mix precision. So it's using the tensor cores that you have in the V100 in the cluster. And instead of representing everything in full precision, it actually allows to represent part of the AI, during the AI training in half precision, and by that speeding up the entire process and allow to have to use less memory. So there's something called automatic mix precision. I won't go into details how to enable this. There are a couple of resources where you can look into it. Some things you have to consider. Just as an example, for Clara Train, the only thing that you have to do is say use AMP. I want to use that. Please take care of the rest for me, and use AMP. So simplifying the features of a GPU in the training network. And so at the beginning, the standardized way of just kicking or defining a training might be a little bit cumbersome. Maybe you're not used to that. However, it allows really nice features. So usually when you train a model, the first parameter set does not work optimally. So there's always room for improvement. It's a very iterative process. So you look for the learning rate, you look for various different parts. So you look for different parameter sets over the time when you develop a model, or also the augmentation pipeline and so on. So by having this information in the JSON file, it's actually easy to iterate over them and modify them. So either you can create manual, various different JSON files and just kick off the training, or for example, you could use the AutoML feature of Clara, which automatically creates these different folders with the different JSON files. You just have to say, okay, I want to look, for example, in this learning range between X and Y. Or I want to see if this augmentation step in this pre-processing pipeline of the imaging pipeline there, for example, actually has an influence. So switching on off a certain transformation. And so making it automatic hyperparameter switch. So this is easy because you actually have this in this folder structure. And here, so for example, add Gaussian noise, probability, yes, no. So you can actually really have everything very modular and look for a different range. And if you want to go crazy and actually want to test something more advanced, there's actual reinforcement learning for you if you want to try it to look into the most probable direction of hyperparameters. So you can also use that. All the results are saved in different folders, and it also shows you which one of these actually gave you the best results according to the metric. And coming back to federated learning, because you have this very structured way of training, it's very usable for federated learning. So you really specify which model, which learning rate, everything in this JSON files, and in a very clear way. So it fits nicely to the federated learning part, and we added the other component to that too. So what Clara Federated Learning brings to you is it takes care of this authentication and giving token of participants. So for example, if you start a federated learning round, the federated learning server locally at your institution says, okay, I know these guys are in this federation in general, but who wants to participate in this federated learning round? Then the client say, well, I want to participate. There's the authentication, it gives the token, it sends the model and so on. So the entire communication process is actually implemented there, and you can just use it. It has the most common federated learning techniques for aggregation, so this federated average. It also has some privacy preserving components, but everything is bring your own component to federated learning. So we always try to have it as flexible as possible. And here just an example. So this is just, it's not the most beautiful one, it's just a screenshot currently. So you have to specify a couple of parameters. But what Clara Federated Learning actually brings you is taking care of the secure connection and certification, takes care of deadlocks or clients that want to join or die in between or want to rejoin. As I said, has a federated average, partial model update sharing, noise model update sharing. And you can also bring your own aggregation method and privacy logic. So if this is a nicer screenshot, so if you have the setup of the server and the clients, what you have to set up for the server is actually here and the clients are in the other one. I won't go into much detail because we're running out of time and soon there might be a new version of Clara Federated Learning. So some parts of this are getting even more easier in future. Just two words on the deployment framework. So everything that you need to deploy an AI model in the hospital environment or in the clinical environment or a healthcare environment. So it takes rather care of the job scheduler, inference manager, has certain pipelines. And so for example, if you read and DICOM, so it's a data format in the healthcare domain, it applies a model, for example, for segment prostate segmentation, has a DICOM writer and also a render server and so on. So also our graphics part is included in there. And just to give you an impression that what else is already in NVIDIA Clara. So if you consider COVID, so one is the medical imaging part. However, we also accelerate the genomics part. So you might have heard from Oxford Nanopore, for example. So they use NVIDIA quite heavily. Or so for the NVIDIA Clara Guardian, everything that has to be done with different sensors. So for example, measuring the temperature or patient monitoring if a patient needs help or falls out of the bed, for example. These things are in Clara Guardian. I'm rushing a bit because we're running out of time. So MONAI is another application framework which has a slightly different focus. So it's also medical specific. So it's a medical open network for AI, short MONAI. And the goal there is to accelerate the pace of research and development by providing a common software foundation and a vibrant community for medical imaging deep learning. So as you can see, the template is not NVIDIA anymore. And I did this on purpose because this is an initiative that we heavily support. We have full-time engineers on that. However, the idea, so it began as a collaboration between NVIDIA and King's College. However, the idea of MONAI is to have it freely available. It's community supported and community driven, PyTorch based, open source, and optimized for medical imaging. So slightly different focus than NVIDIA Clara. And one of the important components is also reference implementation of best practices. Why did we start this? Well, at some point we saw that AI or deep learning training in the medical domain became super important. And there were various different solutions for that. So NiftyNet, DLTK, Clara Train, and they're all valid. However, we brought all of these together and we sat together at the table and said, what if we create a framework that is compatible with the solutions, but brings all the goodness together for the research community in one framework. So that's was the origin of MONAI. And the idea is rather to integrate than compete with the solutions, so bringing the goodness all together and build a community around that. So as I said, provide best practice of AI lifecycle and build a collaborative open source network across academia and enterprise. Just to give you an impression what is in there, it's a lot of foundational components like data, safe and writers, losses, networks that are very common in medical domain, event handlers, and so on. just because we're running out of time, I'm running a bit, sorry. But just to give you an impression that what the difference between MONAI and Clara is. So MONAI is actually really, you use PyTorch, you implement something. So you can also compose a transformation pipeline similar to NVIDIA Clara. However, instead of having this in the JSON file, you actually use the functions here. So you apply these in a list, like here again, you load the image, scale intensity, add channel, and so very similar to that before, but it's again a sequence of operations, but in a different format. And if you want to create, for example, a UNet, one of the most common ones in the medical domain, you can simply create like this. So you have to specify the dimension, the channels, and so on. And a workflow because I showed you the training before in Clara, how you would do this in MONAI is you pip install MONAI, and then you load from the different parts, you compose your transformations, so load, add channel, and so on. For some data sets, we have them available already, so the data loader available there. So this is a Madness dummy data set or a toy data set. And then if you want to train, you specify your trainer in here, and then you run the training. And it's community driven, so we heavily support it. As I said, we have engineers working on that. We are in several of this group. However, it's supposed to be community driven and community supported. So we have an advisory board represented by King's College, Stanford, DCAFSAT, Kitware, TN, and so on. We also have working groups which focus on specific topics like the imaging IO, reproducibility, and community attention. So it's out there since a couple of months. So beginning of this year, we had the first release, first version, and since then it actually got a lot of traction. So we have more than 1,400 stars, GitHub stars, and active contributors. So it's a really growing engagement. And we recently had our first bootcamp for that. We thought we start small and just have a small bootcamp of like 10, 20, 60 maximum participants, and we got more than 500 applications. So there is really, really interest in this community. So we extended it a lot, and we really had a global event from all across the world. So one of the advantages of the current situation, because you can have this virtual community meetings without traveling. So we actually brought together the entire community across the world for this bootcamp, with getting started, with a lot of material for getting started, deeper dive, and so on. We have made this material available online. I will share also the links. So if you're working in the medical domain, please also try this out. And how to engage with MONAI. I won't go into details here. I will share the slides so you don't take screenshots. It's easy if you click on the on the links. So some of the papers that are interesting in the regarding federated learning. If you want to play around with Clara Train, here is the link to the container. We do have Clara Train notebooks. So due to the limited time, I decided not to show you the notebooks, but it's actually hands-on and really nice. So if you want to play around with that, I recommend that. The Clara Federated Learning notebook, I implemented that. However, I would recommend to wait 1-2 weeks because some things might change. And for MONAI, we also, so here on the blog, we have the videos, we have the links to the notebooks, we have the material, everything is available. Okay, we only have a couple of minutes left for discussion, but I hope we have actually some.
Thank you, Nicola. That was very quick, but I think the main value is to give an impression of what is there. And I mean, there is a possibility to make a workshop more in-depth and hands-on. It is totally possible that we can arrange that. So from the attendees, researcher and students, if you feel the need to have hands-on, then please give us the feedback, and then we will make the workshop. Yeah. Then I think we have, I think before going to 1 or 2 questions, I just make a quick announcement right away. So from the poll I sent out. So there are 19 replies, and the proportion that say they can attend monthly is almost twice as the one that say they can attend bi-monthly. So it does indicate that we may do it monthly, and we'll try to keep it that way. Yeah. And so the next question is, what is the next topic? I will try to find that out. For now, then let's do one quick question. I think there is one short question from Peter on the chat. He say, can I program Clara in Python, or is there a library for Python?
So right now there is not. So MONAI is based on Python, and so Clara will support MONAI in the background. So we'll use MONAI as an engine. So in the end, MONAI is constructed. Clara is constructed in a way that it doesn't really matter if you have TensorFlow or PyTorch in the background. It will support Python in the future, in the very, 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 very near future.
Yeah, that's great. Yeah, okay, so I think you also have just answered the question that does Clara support PyTorch model? Yeah.
In future, not right now. So right now it's really based on TensorFlow. In future, it will also support PyTorch models.
Yeah.
And if I say future, it's not in 3 years. So it's actually close future.
Yeah, in a range of months.
Or weeks.
Yeah, yeah. Right. I think, well, for personally, I'm very glad that we made it today, and also thank you everyone for attending. It's a great pleasure to welcome Nicola and Clemens to share with us, and hope to see many more of you next time. And also there's one message from Thomas, the head of AI for the People. He had to leave early, so he want to say thanks for your attendance. Yeah, and also thanks again for Nicola and Clemens. So,
Okay.
Thank you, everyone. Thank you,
Thanks a
Bang.
lot.
thank you. Yeah.
Don't hesitate to reach out if you have any more questions. Okay.
Yeah. Yeah.
Bye-bye.
Thank you. Yeah,
Bye bye.
So for the slides, I will send out later after I get from Nicola.
Perfect.
Yeah.
Bye-bye.
Thank you. Have a good evening.